Hey everybody! There are many ways we can adjust or enhance what we want the player to see on the screen while playing our game. I've already discussed several post-processing algorithms in previous videos, and this time I'd like to add another to the collection, which is quite computationally inexpensive and is something between edge detection and converting a color image into a monochromatic sketch. Let's take a look at it. Like I did last time, or maybe not exactly last time, but in one of the previous videos, I will apply a shader to an image, so instead of the usual color rect, I will create a scene into which I'll drag the mentioned image, which will create a sprite 2D node, like this. Let's create a new scene in the scenes folder, create new scene, let's call it, I don't know, sketch? Yeah, sure. Okay, and now the image I have in the textures folder right here, the usual one, you already know it from previous videos. The sprite 2D node was automatically created, and in the inspector I will cancel centered, and in the transform position I'll reset it to 0, 0. So now it's exactly how we want it. Let's not forget about the shader material in the material section, new shader material, click, and new shader, sketch GD shader of canvas item type, and I'll put it as usual to the shaders folder and create, and click again to open it in the editor. So let's do the usual stuff. I'll delete everything I don't need, which is the vertex function and the light function. Cool. Okay, so as I hinted at the beginning of the video, we'll be doing something like edge detection, which generally involves calculating the difference between the colors of neighboring pixels. However, this time we will have quite sharp edges, because we will use the step function, which takes only values of 0 or 1, depending on the threshold value we use. We will add this value as a uniform parameter and call it cut, because it will indeed be a hard cut with no blurred edges, like in the case of the smooth step function. So let's do it in the code. Uniform float cut with a hint range, and the initial value let's set to 0.9, and it's from 0 to 1 with the step 0.01. Okay, now I will prepare the function getPixel, which will be responsible for comparing the current pixel with its neighbor and will return 0 or 1. I will use the distance function for the comparison, and I will subtract its value from 1 to obtain a result that can be better regularized using the cut parameter. Let's add the function, so it would be float getPixel with parameters sampler 2D, our texture, let's call it text, vector 2 UV coordinates of the current pixel, and the vector 2 offset, because we'll be working with the texture pixel size, which can be different for each image, so we need to pass it as a parameter as well. And we will return, as I said, the step function, a result of the step function with the edge value cut, and the second argument would be 1 minus distance function of our texture, so texture function applied on text and UV coordinates. This is the current pixel, and the second parameter would be again the texture function, but this time, again on the text, but this time a neighboring pixel, so it's UV increased by the offset vector, and that's it. Okay, function is done. And now the fragment function, where we will determine the current size of the pixel in our image and use it to calculate the offset for the getPixel function, like this. I will write the code first, then I will explain it. So let's call it, for example, PS for pixel size, and it's the result of texture pixel size variable. Because I will use it several times, it's better to replace it with a shorter name instead of writing texture pixel size over and over. And then the coordinates UV is UV. This time we don't need to move the origin to the center because we are working with the whole picture and doing this effect on all pixels of this picture. And now float pixel is the function getPixel, getPixel, and the parameter text is our texture, our image we can see right now with UV coordinates. And vec2 we need to define the offset. So the first neighbor is to the right, PSX. We just increase the x coordinate by the texture pixel size x component, and 0 for y. Okay, this is the first one, and now we need to repeat that and multiply the results. So let's just give it some indentation and copy and paste. And this time this would be in the opposite direction, so negative PS to the left. The third one is 0 here, and PSY, which is to the down direction, and finally PS0, 0 in the negative PSY, up, PSY and minus. Okay, so this is the calculation, and finally we can assign the result to the color. So color is vector4, vector3 pixel, and since we are returning either 1 or 0, we will get either a white or black color. There will be no shades of gray. And 1 for alpha. 1. Okay, let's wait for it, and here's the result. Note that the image is indeed composed only of black and white, because as I said, the pixel value becomes 1 only when the result of getPixel function is also 1 in all 4 directions. This time we are comparing the current pixel only with the pixels that neighbor it vertically or horizontally, which is somewhat different from when we compared with pixels that were diagonally adjacent in previous videos. Additionally, we don't have any convolution matrices or Gaussian blur here, so the calculation is very fast and universally applicable. So we can change the cut parameter and observe its effect of on the final result, like here in the shader parameters. Let's make it lower or higher. If it's 1, it's almost everything black, so I guess 0.9 is surely the best value for this parameter. But what if the black and white version of the image isn't enough for us and we want to combine it with the original image? We can see what happens if we subtract this result from the original colors. So let me add something here. It would be texture function of the texture and UV coordinates and only RGB, because we are working with the vector3 here, minus our result. Okay, I would say the result looks quite nice, and the more we decrease the cut value, the darker it will become, like before. Let's just try it. Yeah, because we are subtracting, so the result is darker and darker or lighter, and this is almost the original picture, except something here in the top. Okay, so the result, yeah, as an artistic representation of the scene, I think it can be quite useful. Yes, that's all for now. I apologize for somewhat shorter video, which was mainly due to the fact that most of my time was taken up by work on a new game project that we started at Shadermess Studio. The project is still in a very early stage, but as soon as there is something to showcase, I'll be happy to show it and say a few words about it. For now, thank you for watching, take care, good luck with your own projects, and I'll see you in the next video.